The humble mosquito may seem like a mere annoyance, but it is in fact the deadliest animal on Earth, and the vast majority of these mosquito-related casualties are caused by malaria. Malaria life cycle. A female mosquito bites a human host, and in doing this, the Plasmodium parasite enters the bloodstream. In the human, the parasites move into the liver, infecting the cells where they multiply and mature. Eventually, the liver cell bursts, releasing the parasite into the blood, where they now infect the red blood cells. Again, the parasite multiplies, bursts the cell, and spreads to more red blood cells. This is where all the nasty symptoms show up. At this point, a mosquito can bite the infected person and become infected itself. The cycle continues. Malaria affects 200 million people per year. 600,000 of these die. It also disproportionately affects poorer regions, with 93% of malaria deaths occurring in Africa. Artemisinin is the current frontline treatment for the disease. However, drug-resistant malaria is emerging. If this resistance spreads to Africa, consequences would be devastating. So it's crucial that we develop new drugs to stay ahead of this resistance. This drug needs to kill malaria in a different way to artemisinin, not kill you. Be potent, ideally just one tablet is needed. Be soluble in the bloodstream, and be cheap to manufacture to increase accessibility in poorer countries. Developing new drugs involves the testing of countless compounds, an expensive and time-consuming process currently monopolized by large pharmaceutical companies. So what's the solution? Open source science, built up by lots of little community contributions. We've synthesized 6 compounds with potential anti-malarial properties, all variations on a triazolopyrazine core. First, we performed a condensation reaction. We combined this molecule with our group's designated aldehyde in an ethanol solution. This was done at 40 degrees. We then reacted the resulting chemical at 0 degrees with chloroamine T, and let this reaction continue over a week to form our intermediate. This intermediate was isolated using a separating funnel and a rotating evaporator. Next, we combined the intermediate with toluene and alcohol, using 18 Crown 6 as a catalyst to synthesize our final potential antimalarial. This compound might end up being totally ineffective, but combined with the efforts of researchers around the world, we're creating a global database of potential cures. Compound by compound, we're getting closer to finding a cure for malaria.